It's Chris, the guitar amp tech from Sydney, Australia. It's no great secret that I'm a big fan of the Pro Reverb. In fact, I did a Blackface Pro Reverb, which you can see linked up here. So grab yourself a coffee, pull up a chair, and let's get started on this baby. This is in amazing condition. Look at that faceplate, just a tiny little bit of oxidation on it. Grill cloth is perfect. The Tolex has got a bit of a loose edge up there, which I'll glue down. Bit of a crack here, but otherwise, top and sides look excellent. Let's have a look at the back. So I've pulled off the back plate so we can get a better look in here. And first things that we notice is these speakers look original. And we can see these codes here. Now, I'm assuming you know how to read speaker codes, but if you don't, I'll tell you. So each speaker has its own code somewhere, usually on the frame somewhere. Sometimes I've seen on the cone, but nearly always it's on the frame. And this one is 1377932. So what that means, so 137 is the code for CTS. It's the EIA code, which identifies, speakers, transformers, components from around the world, different manufacturers and who they are. So that we know is a CTS speaker, which was commonly used by Fender. Other ones that you would know are Jensen, so that would have a speaker code of 220. Utah, another common Fender one, probably a bit earlier than this, would be 328. What else would we see? Oxfords we see. Yeah, they're a 465. So they're the main ones that I can barely remember. So this is a CTS speaker. 79 means the speaker was made in 1979, and 32 means the 32nd week. So this would be a late 79 speaker. So we'll check the transformer codes because they have their own EIA codes, and that can help pin it down as well. But I'd be saying this amp would be late 79, early 80. Just based on the speakers alone. JJ's in there, that's fine. We'll give them a test, of course. I'm just curious to see if we've got any gems in here. That's a Sovtech. It's basically these first two that are of the greatest interest to me. Another Sovtech. Okay, so I'm going to assume that they've all been replaced at some stage. I'll put that in once I've got the chassis out. All right, that speaker wire does not look original, and I know because I've done it a squillion times, but I'm just going to put my red nail polish. This is for when I use this colour when I go out on a Friday night. I think red's good for Friday night. And I'm going to put that on the reverb input, just a drop of it on the top there. There we go. And that way, should the owner or someone who can't remember them pull that off, they'll know the red one will go to the red one. I'll see you again on Friday. And the non-original plug, I'm going to pull the chassis out. We'll have a listen to it and see if we can see if there's any issues with it or if it's just a general service, and check the wiring. Now this is an international one. with the adjustable mains selector. I will talk to the owner and see if he would like me to fix it to 240, just so it doesn't accidentally ever get changed. There's normally like a red knob here, and that's been taken off for that same reason of security, I'd be guessing. So I'll ask him if he wants it fixed at 240. And that's, someone's put an Aussie lead on it. That's the shape of Australian lead. And yes, they've got it right. That left-hand pin, when you're looking at the PowerPoint, is should be active, and it's brown, which is active. But we don't like the fact that those leads are just exposed there, so I might see if I can bring that back there a bit. Okay, I'll pull that out and be back with you. Let's have a look and see what's under this capacitor cover. Has it been done recently? Are we going to see some vintage capacitors? Let's have a look. Okay, it has been done. Not overly impressed with the quality of the work or their choice of components. I'll measure them. If I have any doubts about them at all, I'm going to suggest to the owner that we replace them. These are known to be cheap and shitty capacitors, and this is a really tacky workmanship there. What he's done is he's paralleled up these two components. So instead of reading 100 microfarad at 350, we should see 200 microfarad at 350. I guess it was just too hard to order the correct parts. You probably can't see what I'm doing, but I'm using my LCR meter, setting the frequency to 200 to 100 hertz. Clipping that on there, clipping that on there. And we should be seeing 200 microfarad. We are. Let me refer to my ESR table. For a 200 microfarad capacitor at 350, I'd like to see a maximum resistance of 0.5. So this pair in parallel is 0.4, so that is okay, despite being shittily done. 0.4, capacitance likewise, 188, that's still in spec. Now this is 450 volt, 22 microfarad. 22 microfarad, 400. So we want to see a maximum equivalent series resistance of 3 ohms. Yeah, no, not quite. Does 220 ohm sound close to 3? No. Does 4 microfarads sound close to 22? No. So that one is definitely shut itself. In fact, yeah, you can even see the goop oozing out of it. I don't know if you can see it in that camera angle. This one's also got goop, so let's see what the resistance is. The microfarad is close, and this is why you cannot check a capacitor just by testing the microfarad value. You have to check the impedance as well, the ESR as well. Because here, the microfarad value, 24. You could say, oh, that's all right, I'll use that again. But no, its impedance is over double what it should be, the ESR, equivalent series resistance. Have we got any leakage on this one? We don't, so this one may be okay. Yep, that one reads okay. And that, can't see it, but I think it's 100 by 100. 100 microfarad, 100 volts. Let me just refer to the table. 100 by 100, where are you? Should see less than 0.5. That is 0.5. And this one is 0.55. If we were just to replace the ones that had failed, I'd just be replacing these two and this one. But because this is so disgracefully done on such a beautiful amp, and they're using shit capacitors, which means it's just a matter of time before these die as well, I'll put in a quick call to the owner and say, let's replace all of these, do it right with good capacitors that are worthy of this amplifier. I'll suggest either using the MOD caps, which I've had lots of luck with. If we want to keep the cost down a bit, very good, never had a failure with them. Or the F&Ts, which are universally accepted as probably being the best on the market today. I'll talk to the customer and we'll do one or the other. My guess is the previous tech didn't have the correct parts on hand, and instead of ordering the right parts, he did all crazy stuff like this, piggybacking things. I keep just about everything in stock that I'm likely to need, so this is a combination of F&T and Sprague, all top quality brands. He was also paralleled these two 4.7s. That's meant to be a 2.2. I'll replace that with a 2.2. These are okay, so I'll leave those in. Underneath here, we should have some totem resistors, balanced resistors, which also act as a drain to it, and they're meant to balance off these two, which are in series, or these two pairs, which will soon be replaced by one capacitor in each thing. But we still need to that's a bit of a foreign language for you. I speak in tongues, and we need to have a resistor on each leg to balance them off so that the voltage across them, and it's quite a high voltage, I think it's over 500 volts, 550 or something, is equally balanced between the two. We don't want to exceed that. So I'll be replacing all of these and that, put in some balanced resistors, and that's just all too boring for you to watch. So I'll come back to you when it's done. Okay, so the capacitors have been changed, and I just want you to notice that always have the values showing upwards. That just helps the next repairer know what it is. I also like to put a little date sticker under the, where is it? Oh, here. So I put a little date sticker in the lid so that the next tech will know when these capacitors were changed. I replaced that where we had two resistors twisted together, put in the one correct value. Under here I have there's 100k there and 100k there. You can just see the lead there. There to balance the voltage between these two capacitors, which are in series at 300 volts each, because the total voltage across here I think is going to be something like 550 volts. So we can't have it straying too far towards one cap or the other. So those two resistors are essential. They also serve the other purpose of draining these capacitors and all the ones following it when we're turning the system off. So if you can find a tech that does that sort of work and never be ashamed or embarrassed to say, oh, would you mind sending me a couple of photos of what you've done? Never be afraid to ask that question. Anyone who's proud of his work will do it. Anyone that did the work like was what I opened up to will probably not want to show you. Now I'll flip the chassis over and we can see that it's beautifully original. The first thing you notice is this CBS era of wiring is just not up to the standard of the blackface and tweed era and brownface era, but it's still perfectly hand wired. This is a very skilled job. Your average assembly worker can't do this. Could it be better? Yes. Can we make it better? Yes. Will we? No. It's just going to be way too expensive to remove this and reroute these wires properly. But the thing works. So all we want to do is just get a better understanding of it. I spoke to the owner, and he's very happy with the sound of the amp, so we just got to make it sound as good as Fender designed it. So as you can see, nothing here has been changed. Things which can deteriorate that we need to check. Obviously, the cathode bypass caps, we will be checking those. We're really going to hope that our coupling caps are not leaking, because I want to keep as many of these blue caps as possible in here. Late Silverface amps have these two whacking big high wattage resistors in here. Let's just have a quick look and see if we can figure out what they're for. Let's look at this one. This is 10 watt, 2.7K. Check out the voltage that's coming off this solid state rectifier. 520 volts. You can see why they've gone to diode rectification. And 520 volts there. That resistor is going to drop the 500 volts down to 410 volts. 500 to 410, that's 90. We're going to do V squared on R. Divide that by 2,700. So it's 3 watts that is dropping. Fender have given us a 10 watt resistor. Bit of an overkill perhaps. A 5 watt may have done it, but hey, that's better safe than sorry. So that's what that's doing. It's a dropping resistor. So you'd be thinking that's going to drop it to the screen grid. Well, no, it's not dropping it to the screen grid, because this is what they call an UltraLinear. And you'll see here, so here's our B plus coming up here into the center of that transformer, as is normal. And the plates go to either end of the output transformer, as is normal. But this is where it gets a bit abnormal. You'll see here we've got 2 further taps on our output transformer, and they each go via a 470 ohm resistor into the screen grids. So this is called UltraLinear. If you want to have high output, low distortion, you want to keep your screen grids at a constant value. You may know that when we connect the screens directly to the anodes, to the plates, we're effectively in triode mode, which means we have taken out of the circuit the effect of the screen grids. So the screen is there so the electrons are going to flow from the cathode, they're going to flow through the control grid, through the screen grid to the plate. So the control grid, by adjusting how negative it is, like if it goes really negative, there will be no reason for the cathode to emit any electrons. So basically we've turned the tube off. As we go more positive, it's going to attract the electrons away from the cathode, and then the electrons will be attracted towards the plate. If we've taken the screen out of the circuit by hooking it straight to the plate, then the tube's going to be operating less efficiently, because it's going to be looking a fairly big distance to get from the cathode to the plate. If we introduce a screen voltage which is more positive, considerably more positive than the control grid, then the electrons are going to be attracted to go through the control grid. The screen grid is going to go, come on fellas, keep on coming, and they're going to go towards the screen grid. And then the plate, which ideally will be a bit more positive again, will be going, come on, up we come. Let's bring it home. And so they all work in cooperation together, and that makes the tube fairly efficient.
But we want to keep that screen grid fairly constant to maximize the efficiency. And so by taking a specific set value off the output transformer, that's going to be constant, solid as a rock, and it will always provide a constant positive voltage. If we don't, and we take the screen off our plate through a separate dropping resistor like we would do down here in a normal one. So here's an earlier Pro Reverb schematic. So once again, we've got our B plus going to the center of our output transformer, which then goes to the plates of the 6L6s. Then we will either have a choke, as in this case, being a more high-cost premium product, or a resistor, which is also very effective, dropping the voltage down to our screen grid. So obviously the voltage will be a little bit lower. A choke isn't going to drop the voltage very much because its resistance isn't particularly high. It's more there for the inductance rather than the resistance. If we have a resistor, we'll probably see a more significant voltage drop. In this case, the screen will be attached via a dropping resistor there, 470, and another dropping resistor here. So, but in this case, when there is a sudden demand on the plate current, the voltage will drop on the B plus as the power supply supplies that. But because the screen follows the B plus, the screen voltage will also fall, which means its attraction to the electrons will be slightly reduced. Not much, but it will have an effect. With an ultralinear, that screen is going to stay constant all the time, regardless of what's happening with the plate. So even if the plate voltage drops, the screen voltage is still going to stay high, still going to be a high attraction for the electrons to leave the cathode and find its way to the plate. So that was that big resistor there. It's to drop our voltage fairly substantially. Fender at this stage, high volume, and this thing I think is rated, yeah, here we go, so 70 watts, which is a hell of a lot of power to be drawing out of two 6L6s. But in those days, 6L6s, like all our valves, were much better. But so we just got to be mindful of the fact that we're not going to get as long a life out of these two as you would back in the late 70s. Here is that 30K 20 watt resistor. So what's it doing there? It's connected to ground. I had a bit of missing schematic here, so I just filled that in. It's connected to ground. It's also connected to that 2.7K that we just looked at. If you look at it, that 2.7 going to 30K, it's acting like a potential divider. Basically, like this. So there's the 2.7, I'm hoping you can see all this, 2.7 and the 30K. So to figure out that output from that junction there, it's 30K divided by 32.7K times the 500 volt that comes in. And purely, if that's all it was loading that, we would see 30 divided by 32.7 times 500, say 459, say call it 460 volts. Fender have estimated that we'll actually be seeing 410 volts there. So 50 volts, are their calculations out? Well, I don't think so, because we're going to be drawing current, and whenever we draw current, there'll be a voltage drop. We're going to be drawing current to feed the oscillator valve, V5A. What else is going to be fed off this? It's going to go and supply our phase inverter. And where else do we see it? Here. It's going to be supplying the reverb transformer. And if you've ever touched a reverb driver tube, you know how bloody hot that is. So that, so that is going to be drawing a fair bit of current, meaning voltage drop. So that is why we have these high wattage resistors that we didn't see on the earlier Fender amps. It's to do with the very high voltage that's coming off this solid state rectifier. So I'm going to measure these, make sure they're still in spec. I've spoken to the owner and I've told him about my philosophy on repairing these vintage collectible amps is I will only change components that have failed or have drifted significantly away from spec or failure is imminent because of shit, disgraceful choices of replacements. Look at that. What sort of tech would do that? Really? That is just shameful. In that instance, even though that they were fine, they just had to go. I was not going to be putting my name to anything like this. But this is all original. So we're not going to change anything. And I've said to him, we owe this amp to your son and to your grandson so that when he plugs into it in 30 years' time, he's going to know what a 1979 Fender Pro Reverb sounded like. Because if I go changing all of these and putting in orange drops and changing all of the carbon comps and putting in metal films, it might sound great, but it will not sound like a 1979 Fender Pro Reverb. And he was in agreement with that. And so I'm now going to do the rather painful test of every component in here. And I'm going to work, all these carbon comps, they all drift and they all drift upwards. I'm going to allow a 10% variation. If something is 10% or less, it's staying in there. And I know people are going, change them all. I won't. I'm only going to change things that are out by 10%, because I want to keep this as original I can for the owner's son and for the owner's grandson. I was very pleasantly surprised with what I found. I tested every single component except for the coupling caps, which we will test later once we've got power on the circuit. Of course, as we know, every single one of the carbon comps have drifted upwards. There was only a few resistors that failed. Now I had 3, I think, resistors measure out of spec. Interestingly, all of them 1 meg. Now these 2 1 megs here are in the feedback loop of the oscillator tube, and they will basically control the speed of the oscillations. So those combined with these 3 capacitors here will control that oscillation speed. I will not change these until I've got power on it and I can assess the oscillation speed. We have 3 ways of adjusting it. We can either replace these resistors with ones that are in spec, or we can change the values of these 3 capacitors, and quite often I will change this one here to a 0.022 if I want to slow it down a bit. Remembering we're going to try and keep this as original as possible, so at this stage I'm not changing those. I will change this 1 meg because this may impact on the operation of our reverb driver tube. That's not bad. Out of all these resistors, that's the only one that I've got a plan to change. So I'm very happy with that. Now, the capacitors on this side, my fancy schmancy ESR meter tests at all different frequencies. I'm testing filter caps. They're going to be at the rectified frequency of 100 Hertz for Australia, 120 Hertz for the US. But these are more, these cathode bypass caps are not going to be operating at 100 Hertz. They're going to be more operating at guitar signals. So I've decided to go for 400 Hertz, which is one of the settings. So where is that on our guitar? Well, 440 is A, which is the 5th fret on the high E string. So we're going to go 400 hertz. That's the only, I've got options of 800, 400, 1K, 120, 100, etc. So closest I've got to 440 is 400. So these are 25 at 25, 25, that's the closest we got at 25. So I want to see ESR values of less than 2 ohms. So this one here is 22 microfarad, it's supposed to be 25, and it has a ESR of 2.18, and as we just saw, we want to see a maximum of 2, so close to being in spec, I may or may not leave it. This one here, 24, 1.3, obviously that's going to stay. Other techs will automatically replace all of these. Man, if you want me to do that, I'm not. I'm only going to replace what's failed. So if you don't like my approach, maybe find another tech that's happy to do a shotgun replacement on everything. I'm not that guy. Okay, got another cap here. 25 microfarad, measure 23, that's fine. 1.9 is less than 2, that's staying as well. This one here, it's supposed to be 25, it measured at 31 microfarad. So I think we're going to allow 20% for caps. 1.2 by 25, 30, nope, it's going. So I'm going to replace that fella as well. So this one's 5 microfarad at 50 volts. 5 microfarad, that'll do. 60 volts, 63. I should be seeing less than 2 ohms. I'm seeing 6.4. He's going. So all those main filter caps were replaced. The bias caps were replaced, because the previous tech used those really shit IC branded and did such a crappy job in installing. He didn't even put in these what I call totem resistors or series resistors, balance resistors to ensure the equal voltage across those 2 caps. I had another thought as to why this potential divider was put in here. Because our voltages are getting so high in this ultra powerful UltraLinear amp, I think that Fender were very concerned that there would be some upward creep. If this voltage went much higher, a lot of things are going to start going out of spec. So I think that was specifically, these two are there specifically to clamp down that voltage rail. I'd like to check the power wiring. Okay, so the power lead has been replaced. We've got Australian, European colour coding here. So blue is neutral, brown is active. Let me just check that he's got that right. So this is the active. All right, so he's got the colour wiring correct. We have an error here. So blue is neutral, and as we can see, neutral is fused. Nah, that is really dangerously wrong. And here's our active. Active is going to switch. I like the fact that this is switching both active and neutral. I don't like the fact that he's fusing the neutral. Can you tell me why? Correct. Because it is dangerous. Why is it dangerous? If that fuse blows, we still have the active going to the switch. If the switch is on, then we still have the active progressing further into this chassis, into the circuit. So the fuse has to be on the active line. And good practice, legal practice in Australia, and I would assume other countries in the world, is that we have to go from the mains wire to the fuse. We want to connect the incoming mains wire to the back part of the fuse, then out of the fuse. And why is that? So when you unscrew this, if you were to accidentally touch that part with active still on it when you were unscrewing it, it wouldn't be a good day. So it's important that that active come to the back. The fused side then goes to the switch. We also want the neutral wire to go to the switch, and from the switch we're either going to go to the voltage selector if we're using it. The owner has asked me to hardwire it to 240 volts, so I'll do that. So we'll go, the neutral will go from the incoming wire to the switch, to the voltage selector, to the transformer. The active is going to go to the back of the fuse, out of the front of the fuse, to the switch, and onto the transformer. That's going to be another bit of a boring thing, so I might just get that done. Just check this fuse. Slow blow 1.5. Let's have a look at our schematic. And we see here that in the US of A, it's a 2.5 amp fuse, so we would need to halve that, which is like 1.25. Does this give us any more? Well, no, because it's got a whole range of voltages, voltage outputs there. So we're going to go on that, which is I think 1.5 is fine, which is what they had here. Yep, good. So that was also properly spec'd. I'll get on with the boring stuff. Come back once that's done.